Okay, so for loop took 8 seconds. Link also took 8 seconds. Just in case you don't know, for loop performs better than link. It's a different discussion, but link has no performance gain than for loop. So for loop and link took the same 8 seconds. And again, as you can see, link took 4 seconds. So again, we got major performance enhancement by utilizing my multi-core machine. Okay, that's it. Just that easy. So I will show you another example of P-Link, because as I said, P-Link has a lot of extensions. Just as Link. In Link you have select, first, last, as ordered, you have many stuff. In P-Link we also have many extension methods for P-Link. I will show you one of them, which is very important. And using this demo, the next demo, I will explain to you the concept of partitioning. When I started, I talked about partitioning, right? How do you partition? Now I will show you what does this partitioning really means. So I will go to P-Link extensions, which I showed you the solution. Anyway, so this is mainly the same code. Now I have an array of 200 items, okay, and using the as parallel. You remember the as parallel extension, doing the transforming from link to P-Link. And what this code does is that it just prints for me the loop. So it should print for me from 0 to 199. That's it. Now I will run the example. And you should notice something weird. Okay, I'm trying to resize this. Okay. Do you notice something weird here happening? It's the order, right? It did print for me from 0 to 199, which is good. But as you can see, I'm having an ordering problem. So it's 100, 101, 9, 156. The order of the loop was not preserved. Okay? Why is this? To explain this, I will show you I'll go back to the slides and show you this. Okay, so this is how partitioning works. So now in partitioning, as you can see, this is the loop. Okay, it's the enumerator. It's my array enumerator. And as you can see, how P-Links work is that now I have multiple threads. Let's say I have 10 threads working on my array. Each thread will take part of the enumerator. So one thread will take from 1 till 10. Another thread will take from 11 till 30. It depends on how the thread scheduler is working inside .NET 4.0. As I said, .NET 4.0 is handling the partitioning for you. This is partitioning. So I have multiple threads. Each one of these threads took a range of the enumerator, okay, and did the work, separate from each other. Now when all the threads wanted to combine the result back, give me the result back, whichever thread finishes first, gave me the result. Makes sense, okay, it's clear? Okay, so whichever thread finishes first, it gave me the result back. So that's why I saw the unordered results. Okay, so this is one problem of the partition. Now, in some cases, ordering is very important for you. So in some cases, you want to know, so if it's from 0 to 199, you want to preserve the order because your business logic depends on it. Now, what you can do, and again, it's the basic power of P-Link, is that after as parallel, I will use one new extension, which is called as order. Okay? Now I will run the program again. And squeeze this one. Now you can see, try to see, that the printing is in the correct order. Now it's from 0 to 199. So what happened here? What's the difference? I mean, what did this magical method did? The as ordered method, sorry, as ordered extension. It did the following. So now what happened is that the same thing happened at first. I have multiple threads. Each one took a range of my enumerator to operate against. However, what happened is that a new buffer is created. And each thread, while taking the part which it will work on, it memorized the state. So it was, I took the first one, the second thread took the second range, and instead of giving me the result directly back, it inserted the result into a buffer. Now, the execution, I mean the IL if you want, the CLR, took the result from the buffer, rearranged the result, and gave me the result back. Okay? Questions? Too much questions. You have questions related to this? If I don't answer, we will. Okay, please.
Still asynchronous. The process is still asynchronous.
Yes, but it's only using a buffer. Now you might ask me that this buffer will put a overload. Yes, it will. But with everything you do, there's a cost, right? So this buffer definitely has some overload. Okay? Yes. Please.
So I'm not getting the results until all the threads are done.
Yes, in this case, yes. Yeah, that's the cost overload of the buffer. Yes.
You'll have RAM cost also? If you're dealing with large objects or?
Yes, I have one. Sorry.
You will have RAM cost also. You'll add more RAM?
Yeah, you are utilizing a buffer where you are inserting data. I mean, like I said, everything you do has a cost. But sometimes, especially when you are dealing with a large number of iterations, large objects, you'll find the cost is really minimal versus utilizing peeling and utilizing the multiple parallel programs on multiple machines. Okay, so what's my next demo? My next demo is very, very interesting. All my demos are interesting, but this one is very interesting. So I get a question from the gentleman there that, okay, now I'm doing parallel programming and okay, everything is great. But anyone who ever did multi-threading programming knows that life is not that easy. You have something called data races, which requires synchronization, which means inside my for loop, in the previous examples, I always assumed that each iteration of the for loop is doing something independent of the other. So no two tasks, no two threads will fight for a resource. But this is not the case usually. Usually inside the for loop, you are doing some operations where you have a common object or a common variable at least. And once you move from serial programming to parallel programming, you will have each one of the threads fighting for that resource. Okay? Let me show you one. This code, again, it's very simple. Thread.sleep. I'm only sleeping for 1 millisecond, not even 1 second, only for 1 millisecond. And what this code does is that inside each iteration, it does counter plus plus. You all know this code, okay? It takes the counter and plus 1, that's it. So I'm incrementing the counter, and finally in the right line, once the looping finishes, I'm saying print for me the number of times the loop executed. Now, from this code, how much time do we expect if I'm having 100,000 iterations? You will expect counter to be printed how much times? 100,000, okay? However, now you will start dealing with the real-life problems of parallel programming. If I run the code, run the program, sorry, okay. It will take some time to do the iterations. It's working in parallel. Okay, not much CPU utilization, it's only looping. However, if I wait for 14 seconds, it's terminated. Okay, waiting for it to execute again. What you should have saw at the previous screen is that the number printed was not 100,000. It was less. And this number will vary, I mean, from execution to execution. So now the number printed is 99,868, which means that my iteration, not my iterations, but the iterations truly ran 100,000 times. However, the counter was incremented 99,000, blah, blah, blah. Why is this? What's happening here? What's happening here is a classical case of data racing, which requires synchronization. So as I said, if I go back to the code and think a moment about this code. Now I have, let's say, 20 threads operating. I'm not controlling the number of threads. Let's say I have 20 threads operating and parallel. What's happening now is that multiple threads are trying to get access of the counter variable. So something wrong happened. So instead of printing 100,000, I get 99,000 and stuff. One more time to explain this. I will go back to the slides. So why is this? I will explain you just you can read from it. The problem is with the IL, the MSIL, okay, intermediate code that the .NET uses. The IL does not think of counter plus plus as a single line of code. You write